Hello everybody, welcome to Unit 2. Unit 2 is going to be all about the foundations of derivatives. Before we get there, we are going to continue to talk about average rates of change and instantaneous rates of change. So that is 2.1. And so we have looked at these before, but we're going to talk about what average rate of change look a little bit more graphically like today. So when asked to find the average rate of change, you are finding the slope of the secant line. Now, that makes sense if you really think about it, because every single time you've been asked to find the average rate of change, you've been finding the change of y over the change in x. And all that is a slope. So graphically, a secant line is a straight line joining 2 points on a function. And so if you were given 2 points when you were finding the average rates of change, you were just finding the slope between those 2 points. That is what average rate of change is graphically. Instantaneous rate of change graphically is you're finding the slope, but you're finding the slope of the tangent line. The tangent line is a straight line that touches a curve at only 1 point. So like, for example, right here, if I were to find the instantaneous rate of change at 1, I'd be finding the slope of this tangent line right here, but I'm only hitting 1 point of my curve. So here's just a real life example of these different rates. For example, you could take the average speed on an 8-hour road trip. And that would be your average rate of change. You would just take your change in your distance over your change in time. So you could write like change of d over change of t. And so, for example, like if you want 450 miles over 8 hours, your average miles per hour would be 56.25 miles per hour. So that is an example of an average rate of change. But on the other end, kind of same type of example, but with the instantaneous rate of change, that would be your exact speed at exactly 1 hour into your trip. So it would be an exact speed at an exact time. Another example is, say it's raining outside. The average amount of rainfall over 1 hour would be the average rate of change. You would just take the total amount of rain and you would divide that by time. But instantaneous rate of change would be like saying, what is the exact amount of rain falling 25 minutes into a storm? 25 minutes into a storm. So that's an exact time in history. And so let's review real quick the average rate of change before we go more into the instantaneous rate of change. So find the average rate of change from 1 to 3. And we're going to use this function right here. F of x equals -1/2 x minus 3 squared plus 4. And the average rate of change formula is going to be the change in y over the change in x. And so our change in y's, whenever you see something like this, like bracket 1, 3, remember that those are always x values. That's our interval, and intervals are always defined by x values. And so our change in x is going to be 3 minus 1. And now we need to find what our change in y would be. So it'd be f of 3 minus f of 1. We could plug those numbers into our equation, but luckily we're provided the graph over here. So let's figure out the points. So we have 1 here, and this is 1, 2. So that's our x. Our 1 is the x value of our interval, and then 3 is over here. And so I'm basically, by finding the average rate of change, I'm just trying to find the slope of this line, which is just like rise over run, which rise over run is just the change in y over the change in x. This point right here is 3, 4. So f of 3, therefore, is 4. F of 1 is 2, and then my change in my x values is 3 minus 1. So I'd have 4 minus 2, which is 2, 3 minus 1, which is 2, and so our average rate of change is 1, and that is also the slope of this line. So if you look here, if you were to go up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1, that's what you're experiencing when you look at that slope. And so you can do that algebraically, or you can do it graphically. Now we're going to move on to the instantaneous rate of change, and we're going to do this with Desmos. I'm going to post this link on Google Classroom as well if you want to look at this link while you work on these slides. But we're asked to find the average rate of change at x equals 1, and that's a little bit more challenging. Obviously, we know it's the slope of the secant line, we know it's the slope of the tangent line, but it's a little harder to draw the slope of the tangent line accurately, like like you're able to draw the slope of the secant line, because secant line, you're just going between 2 points. Tangent line, you're just at 1 point. So how do you like make your slope? It's a little tricky. And so we're going to use the Desmos. So we basically want to find the average rate of change at 1. So this is 1. So that's our end goal, is to find the average rate of change at 1. But to do that, we're going to explore, well, what would it look like, maybe not to find the average instantaneous rate of change, but let's go back to the average rate. So we're going to start by finding the slope from 1 to 2.5. And I'm going to use different colors as I go. So we're going to start by finding the slope between these 2 points right here. And I could do it all by hand, but luckily I have like a little Desmos thing that's going to make this a little easier for me. So this is that same function. This green point on the left is planted at 1. And so I'm just going to move this second point on the right so that I can find what the exact slope is. So I'm going to move this to 2.5. Right there. Oh, it was really close. I can actually, okay, 2.5 right there. And this is calculating the slope for me, so I don't have to do this a million times. So the slope of this first line right here is 1.25. Now this wants me to find the slope from 1 to 2. So still using this point at 1, because that's where we're trying to find the instantaneous rate of change. And then instead of doing 2, I'm going to do 2.5. So this is what my line's going to look like. If you notice, my line's getting a little steeper every time I go. Okay, and then I'm going to come over here, and I'm going to move, instead of being at the second value being at 2.5, I'm going to move it to 2. See how close I can get. There we go. So the slope there is 1.5 based on that. I'm going to use another color. Let's use purple. Okay, so now I'm going from 1 to 1.5. Notice that these two x values are slowly getting closer and closer together. 1.5, okay, that says the slope is 1.75. And then I need to find one more color. I guess we can use black. And then this says 1 to 1.1, which is going to be really hard to draw, but this is kind of what my graph will look like. Instead of moving this, I can actually come and change this a value to 1, and it will go straight there for me. And it says the slope is 1.95. So 2 things to kind of observe here. The first thing is, if you look at all those lines that I drew, they started out as secant lines, and they still are secant lines, but slowly as I took the second x value and I moved it closer to the first x value, my lines actually became more like tangent lines instead of secant lines. I actually probably didn't draw this last black one very well. It should have probably looked more like this. It was just kind of hard to tell with all these values, but it starts to look more like a secant line or tangent line than it looks like a secant line. It gets steeper and steeper. And then also, if you notice what's happening with these average rates of change is that as we move that second y value or second x value closer to the first one, the gap between the x values is getting smaller. And as that happens, my slopes get closer. What do you guys think they get closer to? You can guess. My slopes get closer to 2, right? It goes from 1.25 to 1.5 to 1.75 to 1.95. So they get closer to 2. And so this says, as we take the average rate of change closer and closer to 1, what we're doing is first we're creating a tangent line. That's what happened as we got those points closer and closer together. And then the slope of the tangent line, what that is, remember, the slope of the tangent line is the instantaneous rate of change. So as we moved it, we started to figure out the instantaneous rate of change. And so what we've been doing this whole time is basically we have been taking a limit. So our average rate of change formula, if you guys remember, is the change of y over the change in x. As we've been making the x values closer and closer together, which means the change between them is getting closer to 0, what you guys might have noticed is that our slope, the change in y over the change of x, was approaching 2. And so as we made our change in x smaller, as we made it so small that it was almost 0, our average rate of change approached 2. And so that right here, 2, is going to be our instantaneous rate of change. We don't actually necessarily see it hit 2, but we watch it approach 2, and that's the idea of a limit. So our instantaneous rate of change is 2. And so on the next slide, I'm going to show you, people have come up with these formulas to help us find the average rate of change. And this is what these formulas were based off of, is that as the gap between these x values gets smaller, we eventually create a tangent line, and we can track the way that these rates of change get closer and closer and closer to a number, and then we can estimate what our instantaneous rate of change is, because we're getting closer and closer and closer and closer to the place that we wanted to find the instantaneous rate of change. So there are some formal definitions that have come up that we're going to start using. And so a formal average rate of change definition is, we've just been doing the change in y over the change in x, so we're going to add a little bit to it. So let's say that we have this graph right here, and we're going to call this first point right here x. I'll use a different color, but we're going to use this first point here. We're going to call this x. And so this value right here is going to be, the x value is x, and then the y value is f of x, because it's the value that goes with x. And then we're going to call this point right here, this x value, we're going to call it x plus h, which is a little weird, but basically that means is it's just h more than our x value. So the distance between these is going to be h, and we're going to call that second x value x plus h. And therefore that means that the x value of this point would be x plus h, and then the y value would be f of x plus h. So if we were then therefore to find the average rate of change over this interval, which is x plus h, so if you were trying to find, I'm going to erase this in a second, but if you were trying to find the slope of this line right here, what we would still do is we're still doing the change in y over the change in x, but with this notation, the change in y would be represented as f of x plus h minus f of x, and the change in x would be x plus h minus x. And then if you were to simplify those denominators, you are going to get those x's. You have x minus x if you look there. So these two x's right here are going to cancel out, and so you would just have h down here. And so with this new formal definition, thinking about the interval as x and then x plus h, that would be what your average rate of change formula would look like. Now, how does that apply to the instantaneous rate of change? Well, we're still going to use the instantaneous rate of change. We're going to do it from x to x plus h, but the instantaneous rate of change is found when the gap between our x values gets smaller and smaller. Right now, h is representing that gap, and so to find the instantaneous rate of change, we're going to find the limit as h approaches 0. So as those two x values get closer, so as this x value and this x value, they get closer and closer and closer together. So we're thinking about the idea of them like moving together, so the gap is getting smaller. So that's why we do the limit as h approaches 0. And then the rest of this formula is just the average rate of change formula. We're just taking the average rate of change over and over again as the gap between those x values gets smaller. So that's one formal definition of average rate of change and instantaneous rate of change. So that's one like mathematical representation you'll see. There's another one that essentially means the same thing that I'm going to show you, but the notation is just a little different. But they do conceptually mean the same thing. So let's say we wanted to think about it a different way. We want to be funky. This time we're going to think about the average rate of change over the interval a and then x. So we'll call this first x value down here, we're going to call this x value a, and we're going to call the second x value x. So that would just be like a and b, right? C and D. Like you're just assigning these x values variables. And so that would mean that this point right here, the x value is a, the y value is f of a. This point right here, the x value is x, the y value is f of x. Okay, and so then the average rate of change formula would be the change in y, which is f of x minus f of a all over x minus a. So that would be what the average rate of change formula is. And then the instantaneous rate of change formula would be the limit as x approaches a. Now the reason it's the limit as x approaches a is because as x gets closer to a, the likelihood of this denominator right here, x minus a, that is going to get closer to 0. For example, like let's say that a was 3, okay? If x is approaching a, so let's say that x is 3.5, 3.5 minus 3 is 0.5. Let's say that x is continuing to approach a. Let's say it's 3.4. Minus 3 is 0.4, right? Say it's 3.3. So as it gets closer to that value, the gap between them is getting smaller. And so this formula is going to be the limit as x approaches a of f of x minus f of a all over x minus a. So that's how people came up with that one. They're basically just taking the average rate of change over and over again as the x value approaches a, therefore the gap between them gets smaller. And so that's just the same concept of the limit. We're just approaching something. So we're just approaching these x values. Okay, so what do we do to actually solve these problems? Well, we are going to do an example of solving these problems with both of the definitions. So we're going to start with the first definition. So the first definition was the limit as h approaches 0 of f of x plus h minus f of x over h. And so this is how we can find the instantaneous rate of change. This is our first definition. And we want to find the instantaneous rate of change of f of x equals x squared at x equals 2. So we know that the place that we're finding this change is at 2. So what we can go ahead and do in this formula is, because we know that x is going to equal 2, we can go through and replace our x values with 2. So we can go ahead and replace these x values with 2, because that is where we're trying to find the instantaneous rate of change. That's where we're trying to find the slope of the tangent line. All of those words, those phrases just can be intertwined because they mean the same thing. Now we are going to use function notation. So if I am going to do this right here, I'm going to do the limit as h approaches 0. That limit as h approaches 0 part does not go away until you plug in 0 for h. I am going to go ahead and put these expressions into my function. I'm going to use function notation. So f of 2 plus h, I am going to take 2 plus h, and I am going to plug in 2 plus h for x, because that is function notation. So I'm going to do 2 plus h squared. And that's what f of 2 plus h is. I'm going to write this over here. So f of 2 plus h is equivalent to 2 plus h squared, because f of x equals x squared. So that's how I'm getting that. Then if I want to subtract f of 2, I'll just do f of 2, and then I'll plug in 2 for x, and that'll be 2 squared. So I'll do minus 2 squared all over h. And that is what I get right now. So I've done my step, and I put these things into the function. Now, if I were to plug in 0 right now, I'm going to show you what would happen. If I were to plug in 0 for h, I would have 2 plus 0 squared minus 2 squared all over 0. 2 plus 0 squared is 2 squared, and that's 4. 2 squared is 4, so I'd have 4 minus 4 over 0, and I would get 0 over 0. So I get indeterminate form, which is what we did in Unit 1. And so I need to figure out, is there a way that I could manipulate or simplify so that I'm canceling out the factor that's making us divide by 0. So what we're going to do is, let's just clean up the numerator a little bit. Let's distribute. So I'm going to do 2 plus h. 2 plus h squared is the same as 2 plus h times 2 plus h, and then 2 squared is 4, so I'm just going to go ahead and write minus 4 all over h. Likely I'm trying to cancel out the h on the bottom because that's making us divide by 0. I'm going to distribute my numerator. So I'll do 2 times 2, which is 4. 2 times h, which is 2h. H times 2, which is 2h. And then h times h, which is h squared. I'm going to subtract 4 because of that 4 over there, and I'll divide it all by h. If I clean up that numerator, these 4's will cancel out because I have a 4 minus a 4. I'm going to write h squared. Hold on, someone needs me. Okay, sorry, I'm back. Someone just knocked on my door. Okay, so continuing to simplify. So this will be h squared. That comes down, and then 2h plus 2h equals 4h. And so now I have h squared plus 4h over h. Maybe you'll see where this is going. But if you look at the numerator, there is a common factor there. And so I can pull out h from the numerator, and that will leave me with h plus 4. So I'm just factoring. And then these two h's, voila, can go away. And I cross out the factor that was making me divide by 0, and I'll have the limit as h approaches 0 of h plus 4. Now I can plug in 0. I get 0 plus 4, and that equals 4. And that was a lot of work, but that is my instantaneous rate of change at x equals 2. We have to learn how to do it this long way, but eventually we will learn a shortcut to doing these problems. But right now, we're going to do it the long way because it helps us understand why is this the instantaneous rate of change? How did we come up with this formula, etc. So going on to the next one, we only have one more like long example like this, and then we'll just do one short example where we set it up, but we don't solve the problem. So this one says find the instantaneous rate of change of f of x equals 3x squared plus 4 at a equals 9, and we'll use the second definition. So the second definition is the limit as x approaches a of f of x minus f of a over x minus a. So the first thing I'm going to do with this definition is that we're concerned about finding the instantaneous rate of change, specifically at a equals 9. So I'm going to replace my a values with 9 because that's where I want to find the rate of change. So anywhere there was an a value, I'm replacing that with 9 now. Now I'm going to actually use function notation and actually plug these things into my function. So we'll have the limit as x approaches 9. F of x is 3x squared, so I'm going to put 3x squared there. And then I'm going to plug in 9 into 3x squared. So I'll have 3 times 9 squared. Oh, but it's plus 4. So I made a mistake. So that was good that I made that. I forgot the plus 4. So f of x is actually 3x squared plus 4. And then you're subtracting 3 times 9 squared plus 4. All over x minus 9. Now, I've plugged everything in. Everything is great. But if I were to plug in 9 right now, I would get indeterminate form. So that means I'm going to have to clean some things up. There's a chance I'm going to have to factor. But eventually, I will get the correct answer. All of these, at least all of the polynomial ones will always work out. Sometimes there's a good amount of work to do, but it will always work out. So the limit as x approaches 9, I'm going to clean some of this stuff up. So I'm going to drop the parentheses because I don't really need them. And then I'm going to simplify what's inside these parentheses. So 9 squared is 81. 3 times 81 is 243. And then 243 plus 4 is 247. And then I will get the limit as x approaches 9 of 3x squared minus 4 minus 247, which is going to, oh, sorry, this should have been plus 4. So 3x squared plus 4 minus 247, which will be 243. And again, I haven't crossed out any factors. Oh, sorry, x minus. I haven't crossed out any factors yet, so I can't plug in 9 yet. It still is not going to work. But if I look at the numerator, I can pull out a greatest common factor because 3 goes into 3x squared and it goes into 243. 243 divided by 3 is 81. I'll have x minus 9. Still, nothing cancels out, but if you look at the numerator, that is a difference of perfect squares. So you'll have 3 times x minus 9 times x plus 9 all over x minus 9. And now the factor on the denominator and the numerator can cancel out. So we cancel out the thing that was making us divide by 0. And we'll get 3 times x plus 9. Since we canceled out the factor that was making us divide by 0, we can go ahead and plug in 3. And we will get 3 times 12, which equals, oh, sorry, this is a 9. I changed this to a 9. Limit as x approaches 9. Limit as x approaches 9. So then I can plug in 9 here. Sorry about that. Oops. So I'm plugging in 3 times 9 plus 9, which equals 3 times 18, which is 54. So the average rate of change at 9 of 3x squared plus 4 is 54. We're going to do one more example real quick, but again, we're not going to solve this problem. We're just going to set it up. So we have this cat. Her name is Estelle, and she's riding a helicopter. The altitude of her helicopter is given by E of t equals negative 11 t squared plus 900 t. E of t is measured in feet and t in minutes after takeoff. Sorry, this is typo city, but write 2 expressions, one in each form, to represent the instantaneous rate of change of Estelle's helicopter ride at t equals 12. So I'm going to split this into 2. I'm just going to write the expressions. I'm not going to solve for them. But remember, our first definition of the limit is the limit as h approaches 0 of f of x plus h minus f of x all over h. And then the other one is the limit as x approaches a of f of x minus f of a all over x minus a. So I go over to this first one. I'm concerned about Estelle's helicopter ride, specifically at t equals 7. So I'm going to go ahead and plug in t for all of the places. So I'm going to plug in, and this is just t is our variable. So we can also think about this as x. So I'm going to plug in 7 for all the x values. So f of 7 plus h minus f of 7 all over h. And then I'm going to take this function and I'm going to plug it into our function, which is negative 11t plus 900t. So I'm going to do, and I'm going to put this in parentheses really to keep it organized. I'm going to do negative 11 times 7 plus h squared plus 900 7 plus h. And then I'm going to subtract that by negative 11, 7 squared, plus 900 times 7 all over h. So I just plugged it in. That's all I want with your expression. You don't need to go further than that. So that is the first example of the expression. The other one, we're going to find the limit as, so t is 7, but we can also think about that as a. So as x approaches 7 of f of x minus f of 7 all over x minus 7, and then I'll just plug things into that function. A lot of times people prefer this other one because it looks simpler. So f of x, or in this case e of t, because that's the function we're using, is going to be negative 11t squared plus 900t. So that's the first expression minus the second expression, which is just the first one with 7 plugged in. So negative 11 times 7 squared plus 900 times 7. And then all over x minus 7. And that's it. And sorry, we'll do a t since I was using t's up there. T minus 7. And then therefore this would need to change to a t. So that is your final answer. If the variables over here are kind of confusing you, just let me know and I can kind of explain more in person. But that is how we do these problems. We're going to continue to practice. There are a lot to take in, but eventually we'll get some shortcuts. So have a good day. Bye.